Relativity, the Special and General Theory, by Albert Einstein. Section 18. Special and General Principle of Relativity. The basal principle, which was the pivot of all our previous considerations, was the special principle of relativity, i.e., the principle of the physical relativity of all uniform motion. Let us once more analyze its meaning carefully. It was at all times clear that, from the point of view of the idea it conveys to us, every motion must be considered only as a relative motion. Returning to the illustration we have frequently used of the embankment and the railway carriage, we can express the fact of the motion here taking place in the following two forms, both of which are equally justifiable. A. The carriage is in motion relative to the embankment. B. The embankment is in motion relative to the carriage. In A, the embankment, in B, the carriage, serves as the body of reference in our statement of the motion taking place. If it is simply a question of detecting or of describing the motion involved, it is in principle immaterial to what reference body we refer the motion. As already mentioned, this is self-evident, but it must not be confused with the much more comprehensive statement called the principle of relativity, which we have taken as the basis of our investigations. The principle we have made use of not only maintains that we may equally well choose the carriage or the embankment as our reference body for the description of any event, for this too is self-evident. Our principle rather asserts what follows. If we formulate the general laws of nature as they are obtained from experience by making use of A. The embankment as reference body, B. The railway carriage as reference body, then these general laws of nature, e.g., the laws of mechanics, or the law of the propagation of light in vacuo, have exactly the same form in both cases. This can also be expressed as follows. For the physical description of natural processes, neither of the reference bodies K, K' is unique, literally specially marked out, as compared with the other. Unlike the first, this latter statement need not of necessity hold a priori. It is not contained in the conceptions of motion and reference body and derivable from them. Only experience can decide as to its correctness or incorrectness. Up to the present, however, we have by no means maintained the equivalence of all bodies of reference K in connection with the formulation of natural laws. Our course was more on the following lines. In the first place, we started out from the assumption that there exists a reference body K, whose condition of motion is such that the Galilean law holds with respect to it, a particle left to itself and sufficiently far removed from all other particles moves uniformly in a straight line. With reference to K, Galilean reference body, the laws of nature were to be as simple as possible. But, in addition to K, all bodies of reference, K', should be given preference in this sense, and they should be exactly equivalent to K for the formulation of natural laws, provided that they are in a state of uniform rectilinear and non-rotary motion with respect to K. All these bodies of reference are to be regarded as Galilean reference bodies. The validity of the principle of relativity was assumed only for these reference bodies, but not for others, e.g., those possessing motion of a different kind. In this sense we speak of the special principle of relativity, or special theory of relativity. In contrast to this, we wish to understand by the general principle of relativity the following statement. All bodies of reference K, K', etc., are equivalent for the description of natural phenomena, or formulation of the general laws of nature, whatever may be their state of motion. But before proceeding farther, it ought to be pointed out that this formulation must be replaced later by a more abstract one, for reasons which will become evident at a later stage. Since the introduction of the special principle of relativity has been justified, every intellect which strives after generalization must feel the temptation to venture the step towards the general principle of relativity. But a simple and apparently quite reliable consideration seems to suggest that, for the present at any rate, there is little hope of success in such an attempt. Let us imagine ourselves transferred to our old friend the railway carriage, which is traveling at a uniform rate. As long as it is moving uniformly, the occupant of the carriage is not sensible of its motion, and it is for this reason that he can without reluctance interpret the facts of the case as indicating that the carriage is at rest but the embankment in motion. Moreover, according to the special principle of relativity, this interpretation is quite justified also from a physical point of view. If the motion of the carriage is now changed into a non-uniform motion, as for instance by a powerful application of the brakes, then the occupant of the carriage experiences a correspondingly powerful jerk forwards. The retarded motion is manifested in the mechanical behavior of bodies relative to the person in the railway carriage. The mechanical behavior is different from that of the case previously considered, and for this reason it would appear to be impossible that the same mechanical laws hold relatively to the non-uniformly moving carriage as hold with reference to the carriage when at rest or in uniform motion. At all events, it is clear that the Galilean law does not hold with respect to the non-uniformly moving carriage. Because of this, we feel compelled at the present juncture to grant a kind of absolute physical reality to non-uniform motion, in opposition to the general principle of relativity. But in what follows we shall soon see that this conclusion cannot be maintained. Section 19. The gravitational field. If we pick up a stone and then let it go, why does it fall to the ground? The usual answer to this question is, because it is attracted by the earth. Modern physics formulates the answer rather differently for the following reason. As a result of the more careful study of electromagnetic phenomena, we have come to regard action at a distance as a process impossible without the intervention of some intermediary medium. If, for instance, a magnet attracts a piece of iron, we cannot be content to regard this as meaning that the magnet acts directly on the iron through the intermediate empty space, but we are constrained to imagine, after the manner of Faraday, that the magnet always calls into being something physically real in the space around it, that something being what we call a magnetic field. In its turn, this magnetic field operates on the piece of iron, so that the latter strives to move towards the magnet. We shall not discuss here the justification for this incidental conception, which is indeed a somewhat arbitrary one. We shall only mention that with its aid electromagnetic phenomena can be theoretically represented much more satisfactorily than without it, and this applies particularly to the transmission of electromagnetic waves. The effects of gravitation also are regarded in an analogous manner. The action of the earth on the stone takes place indirectly. The earth produces in its surroundings a gravitational field, which acts on the stone and produces its motion of fall. As we know from experience, the intensity of the action on a body diminishes, according to a quite definite law, as we proceed farther and farther away from the earth. From our point of view this means, the law governing the properties of the gravitational field in space must be a perfectly definite one, in order correctly to represent the diminution of gravitational action with the distance from operative bodies. It is something like this. The body, e.g. the earth, produces a field in its immediate neighborhood directly. The intensity and direction of the field at points farther removed from the body are thence determined by the law which governs the properties in space of the gravitational fields themselves. In contrast to electric and magnetic fields, the gravitational field exhibits a most remarkable property, which is of fundamental importance for what follows. Bodies which are moving under the sole influence of a gravitational field receive an acceleration which does not in the least depend either on the material or on the physical state of the body. For instance, a piece of lead and a piece of wood fall in exactly the same manner in a gravitational field in vacuo, when they start off from rest or with the same initial velocity. This law, which holds most accurately, can be expressed in a different form in the light of the following consideration. According to Newton's law of motion, we have force equals inertial mass times acceleration, where the inertial mass is a characteristic constant of the accelerated body. If now gravitation is the cause of the acceleration, we then have force equals gravitational mass times intensity of the gravitational field, where the gravitational mass is likewise a characteristic constant for the body. From these two relations follows acceleration equals the fraction gravitational mass over inertial mass times intensity of the gravitational field. If now, as we find from experience, the acceleration is to be independent of the nature and the condition of the body, and always the same for a given gravitational field, then the ratio of the gravitational to the inertial mass must likewise be the same for all bodies. By a suitable choice of units, we can thus make this ratio equal to unity. We then have the following law. The gravitational mass of a body is equal to its inertial mass. It is true that this important law had hitherto been recorded in mechanics, but it had not been interpreted. A satisfactory interpretation can be obtained only if we recognize the following fact. The same quality of a body manifests itself according to the circumstances as inertia or as weight, literally heaviness. In the following section we shall show to what extent this is actually the case, and how this question is connected with the general postulate of relativity. Section 20. The equality of inertial and gravitational mass as an argument for the general postulate of relativity. We imagine a large portion of empty space, so far removed from stars and other appreciable masses, that we have before us approximately the conditions required by the fundamental law of Galilei. It is then possible to choose a Galilean reference body for this part of space, world, relative to which points at rest remain at rest, and points in motion continue permanently in uniform rectilinear motion. As reference body, let us imagine a spacious chest resembling a room with an observer inside, who is equipped with apparatus. Gravitation naturally does not exist for this observer. He must fasten himself with strings to the floor, otherwise the slightest impact against the floor will cause him to rise slowly toward the ceiling of the room. To the middle of the lid of the chest is fixed externally a hook with rope attached, and now a being, what kind of a being is immaterial to us, begins pulling at this with a constant force. The chest, together with the observer, then begin to move upwards with a uniformly accelerated motion. In course of time their velocity will reach unheard of values, provided that we are viewing all this from another reference body which is not being pulled with a rope. But how does the man in the chest regard the process? The acceleration of the chest will be transmitted to him by the reaction of the floor of the chest. He must therefore take up this pressure by means of his legs if he does not wish to be laid out full length on the floor. He is then standing in the chest in exactly the same way as anyone stands in a room of a house on our earth. If he release a body which he previously had in his hand, the acceleration of the chest will no longer be transmitted to this body, and for this reason the body will approach the floor of the chest with an accelerated relative motion. The observer will further convince himself that the acceleration of the body towards the floor of the chest is always of the same magnitude, whatever kind of body he may happen to use for the experiment. Relying on his knowledge of the gravitational field, as it was discussed in the preceding section, the man in the chest will thus come to the conclusion that he and the chest are in a gravitational field which is constant with regard to time. Of course, he will be puzzled for a moment as to why the chest does not fall in this gravitational field. Just then, however, he discovers the hook in the middle of the lid of the chest, and the rope which is attached to it, and he consequently comes to the conclusion that the chest is suspended at rest in the gravitational field. Ought we to smile at the man and say that he errs in his conclusion? I do not believe we ought to if we wish to remain consistent. We must rather admit that his mode of grasping the situation violates neither reason nor known mechanical laws. Even though it is being accelerated with respect to the Galilean space first considered, we can nevertheless regard the chest as being at rest. We have thus good grounds for extending the principle of relativity to include bodies of reference which are accelerated with respect to each other, and, as a result, we have gained a powerful argument for a generalized postulate of relativity. We must note carefully that the possibility of this mode of interpretation rests on the fundamental property of the gravitational field of giving all bodies the same acceleration, or, what comes to the same thing, on the law of the equality of inertial and gravitational mass. If this natural law did not exist, the man in the accelerated chest would not be able to interpret the behavior of the bodies around him on the supposition of a gravitational field, and he would not be justified on the grounds of experience in supposing his reference body to be at rest. Suppose that the man in the chest fixes a rope to the inner side of the lid, and that he attaches a body to the free end of the rope. The result of this will be to stretch the rope so that it will hang vertically downwards. If we ask for an opinion of the cause of tension in the rope, the man in the chest will say, "The suspended body experiences a downward force in the gravitational field, and this is neutralized by the tension of the rope. What determines the magnitude of the tension of the rope is the gravitational mass of the suspended body." On the other hand, an observer who is poised freely in space will interpret the condition of things thus: the rope must perforce take part in the accelerated motion of the chest, and it transmits this motion to the body attached to it. The tension of the rope is just large enough to effect the acceleration of the body. That which determines the magnitude of the tension of the rope is the inertial mass of the body. Guided by this example, we see that our extension of the principle of relativity implies the necessity of the law of the equality of inertial and gravitational mass. Thus we have obtained a physical interpretation of this law. From our consideration of the accelerated chest, we see that a general theory of relativity must yield important results on the laws of gravitation. In point of fact, the systematic pursuit of the general idea of relativity has supplied the laws satisfied by the gravitational field. Before proceeding farther, however, I must warn the reader against a misconception suggested by these considerations. A gravitational field exists for the man in the chest, despite the fact that there was no such field for the coordinate system first chosen. Now we might easily suppose that the existence of a gravitational field is always only an apparent one. We might also think that, regardless of the kind of gravitational field which may be present, we could always choose another reference body such that no gravitational field exists with reference to it. This is by no means true for all gravitational fields, but only for those of quite special form. It is, for instance, impossible to choose a body of reference such that, as judged from it, the gravitational field of the earth, in its entirety, vanishes. We can now appreciate why that argument is not convincing, which we brought forward against the general principle of relativity at the end of section 18. It is certainly true that the observer in the railway carriage experiences a jerk forwards as a result of the application of the brake, and that he recognizes in this the non-uniformity of motion, or retardation, of the carriage. But he is compelled by nobody to refer this jerk to a real acceleration, or retardation, of the carriage. He might also interpret his experience thus: my body of reference, the carriage, remains permanently at rest. With reference to it, however, there exists, during the period of application of the brakes, a gravitational field which is directed forwards and which is variable with respect to time. Under the influence of this field, the embankment, together with the earth, moves non-uniformly, in such a manner that their original velocity in the backwards direction is continuously reduced. End of section 20.